Now, there are other applications of this rule. The next one that I want to look at is what happens if I'm taking a limit, quotient of two different functions, but now each of these functions doesn't actually have a limit as x goes to a. Maybe f of x goes to positive infinity, or f of x goes to negative infinity. Maybe g of x goes to negative infinity. Maybe g of x goes to positive infinity. But both of these limits fail to exist. Then I'm stuck in this same situation where I cannot use direct substitution again. So this gives me a second kind of indeterminate form of infinity divided by infinity. Well, in that situation, I can still use L'Hopital's rule. So as long as these functions are both differentiable and the derivative of g of x is not 0 when we're close to my target coordinate, we can try to calculate this new limit instead, the limit as x goes to a of f prime of x divided by g prime of x. If that new limit exists, then the old limit has to be equal to the new limit. If the new limit is plus or minus infinity, then the original limit also has to be plus or minus infinity with the same sign, of course. Now, why does this actually work? My situation is that f of x is tending towards infinity or possibly minus infinity. G of x is also tending towards infinity or possibly minus infinity. So I'm going to rewrite this fraction as 1 on g of x all on 1 on f of x. So just a little bit of trickery with the way that I've chosen to express my quotient, but it's exactly the same result. Well, that means that 1 on f of x is my new denominator, and it's going to 0. My new numerator, 1 on g of x, is also going to 0. So I can use L'Hopital's rule because I've got my 0 on 0 situation. So this is sort of the bird's eye view here. There's some technical details to clean up, but you can find those in the appendix to our textbook. Let's actually use this formula on a problem. Let's calculate the limit as x goes to infinity of e to the power 2x all on x. So each of these functions, the numerator and the denominator, go to positive infinity as x goes to infinity. So we are allowed to use L'Hopital's rule to say, well, this is, well, the derivative of my numerator is 2e to the power 2x. The derivative of my denominator is just 1. So I'm going to calculate a different limit, where I'm taking the limit of the derivative of the old numerator divided by the derivative of the old denominator. And this limit as x goes to infinity of 2e to the power 2x all on 1, well, that's going to go to positive infinity. Since my numerator is increasing without bound, my denominator is just a 1, so I can just ignore that. And since this limit, my new limit here, goes to positive infinity, then L'Hopital's rule tells me that the old limit also goes to positive infinity. So we can get a lot of mileage out of L'Hopital's rule if you see an indeterminate form, so like a 0 on 0 kind of limit, or an infinity on infinity kind of limit, or even other indeterminates, like what if you have a limit of the product of two functions, the one of them goes to 0, the other of them goes to infinity, you can still do this kind of trick to rewrite the formula inside the limit and still end up using L'Hopital's rule. So this is a very useful technique for calculating limits of functions that otherwise we just wouldn't be able to get a grip on.